Good morning. So today I'll talk about another topic advertised in the title of these lectures, which is cover times. And the main topic is based on joint work with Jian Ding, who is starting this year in the University of Chicago, but was still a student at Berkeley when we did this work. And James Lee, who's a professor at the University of Washington Computer Science Department. So we're going to be considering random walk on a graph. So simple random walk on a graph. Everything I described today works also for any reversible Markov chain. Any such chain you can obtain by taking a graph, putting conductances on the edges, and then taking a walk where the probability of every step is proportional to the conductances. So you can do that. If all the conductances are 1 on the edges, you just get simple random walk, and the formulas look a little bit simpler. So in the talk, I'll just discuss this special case. The objects we're interested in are mostly the cover time, the time it takes for a random walk to visit the whole graph. And these are related to two other notions, the local times, which are the normalized number of visits to a site. So on this picture here, you see a random walk on a large square with periodic boundary conditions, run for a long time, and the colors represent the number of visits to every site. No, I have. Is it? Okay. This can have a duel here. So these local times represent the number of visits to a site. Later we'll want to normalize by the degree. Here all the degrees are the same. So this is the picture representing the local times. Here we ran the random walk until it visited all the sites, and here the colors represent the hitting times, the number of steps it took until we visited a certain site. And both of these exhibit interesting fractal structure when we do this on tori, especially in 2 dimensions. And this fractal structure has been subject of a lot of research, both in mathematical physics and in probability. This won't be my emphasis for today, because that is restricted to lattices mostly, and I'll want to get to talk about more general graphs where the estimates are of different nature. Okay, so here's some notation. So h of uv is the expected number of steps to hit a vertex v starting at u, and these hitting times are nice in several ways. One, they can be computed, as I'll recall. Second, they satisfy a triangle inequality. So obviously the hitting time from u to w is bounded by the hitting time from u to v plus the hitting time from v to w, right? Because that's one way to go. So they satisfy a triangle inequality, but they're not symmetric, as you can easily see, even if the transition matrix is symmetric, the hitting times are not. So one thing we can do is symmetrize them. So we get the commute times, time to go from u to v and back to u, the expected time. And these still inherit the triangle inequality from the hitting times. And now they are a metric, okay? Because obviously it's 0 only if u equals v. And it turns out to be a very useful metric. I'll come to that later. Now, the star of our show will be the expected cover time, the expected time to visit all the vertices of G. Now, this, of course, can depend a bit on the starting point. So to be concrete, we're going to maximize over the starting point. Now, just to get our bearings, here are orders of magnitude of cover times on some standard graphs. So for a path, just going from left to right is n squared steps. For a complete graph, cover time is just the coupon collector problem. So we know it's n log n. Now, on any expander graph, these are graphs where the spectral gap is bounded away from 0. So lambda 2 that we discussed is bounded away from 1. On these, the cover time is still n log n. One interesting example I've worked on a lot is just the two-dimensional grid. So you have a two-dimensional grid with n points, so root n by root n. You can, it doesn't matter if you do it periodic boundary conditions or free. And look at the time it takes to cover that. So that's, there is an extra log, so it's n log squared n. And that's not hard. There are nice techniques to do that. That was done in the late 80s. And then to understand the fractal structure I described to you before, one needs to really pin down the constants in front. And this involves a lot of work. And that was work with Dembo, Rosen, Zeytouni about 10 years ago, which gave that fractal structure I showed you in the picture. In the three-dimensional grid, it's back to behaving like the complete graph, so it's order n log n. However, if you take a regular tree and just truncate it after finitely many levels, so you have n points, then it behaves like a two-dimensional grid. So this actually is an important connection we'll come back to. So in the this corresponds to the fact that in the two-dimensional grids, all scales somehow have the same importance, while well, yes.
And like 4 or 5-dimensional grid is the same as
yeah. 3 and higher are all the same. Yes. So right. So okay. So right. So okay. So in one dimension, somehow it's just the global structure that matters. In 3 dimensions, it's just the local, and 2, it's exactly where there's balance between global and local. But okay, let me go on. So so we define these basic notions. Now here are the general bounds, where n is the number of vertices and E is the set of edges. So the cover time is always at least n log n. This is actually not trivial at all. So Matthews gave a nice argument to show this up to constants. But to pin down the constant took a very clever argument by Uri Feige in '95. By the way, Uri is a computer scientist, and computer scientists have been very interested in this issue because cover time represents a determination time for various natural exploration algorithms. On the other hand, there are some general upper bounds. So one going back a long time is the product of the number of edges times the number of vertices. And this is based on a nice argument, taking the graph, putting a spanning tree inside, and just saying, well, one way to cover the graph is just to cross all the edges of the spanning tree in kind of a depth first search where we cross every edge twice. So this kind of tour would certainly cover the graph. And so we can bound the cover time by the sum of the commute times on all the edges of the spanning tree. And if we do that and use kind of known formulas for commute times, we get this bound. So it seems like this bound is very wasteful, but in fact, up to constant, it's the right upper bound. So actually, the worst upper bound, the largest cover time on the graph of n edges is n cubed with this constant in front. Again, the constant was pinned down by Feige. Okay. Now, I told you that the commute time is an interesting metric, and it's closely related to the effective resistances. In fact, up to constant, it's the same. So the effective resistance in a graph has several equivalent interpretations. One is you try to send a unit flow from the vertex U to the vertex V in the graph. So you root a unit flow, and you look at the energy of the flow, so the sum of the squares of the flows along all the edges. And you try to minimize that among all unit flows. So you're basically trying to distribute the flow as uniformly as possible so the sum of squares will be minimized. And this minimal energy is the effective resistance. There's a beautiful connection of the effective resistance to the commute time, as I said, up to twice the number of edges that are the same. So those who haven't worked with effective resistance can think of this as a definition of effective resistance. But of course, to really work with it, you need to work with the many definitions. Okay, and there's exposition of this theory in many places, like the famous high school level beautiful book by Doyle and Snell, or I've written a book on Markov chains, and so on. And there are many other places. Okay, so now we're going to approach to the cover time from a computational point of view. So let's first look at the heating times. So heating times are very easy to compute because they satisfy linear equations, right? The heating time from U to V, well, if U and V are different, you take one step from U, and then you have to go from some neighbor of U to V. So this is the average of the heating times from W to V. And these linear equations, it's easy to check that this is a regular system of equations, so they completely characterize the heating times. Now, what about the cover time, time to visit all vertices? If you want to compute it, well, one way you could just run the random walk many times. On average, you'd get some statistical estimate. But if you want to compute it deterministically exactly, you can do it by a heating time computation, but on a very large space. That is, if you look at a Markov chain where the states are the set of nodes we visited so far together with where we are now. So this is an exponential state space. But in this state space, the cover time corresponds to the time that this huge Markov chain hits the collection, the state where, well, the vertices we visited is the whole graph. So you can get it by a heating time calculation, but on an exponentially sized graph, so it's not very useful. And the question was, can you do something in reasonable time, polynomial time? This question was raised by Aldous and Phil, and even beyond computing it exactly, just estimate it up to a constant factor, but deterministically for sure, without statistical error, in polynomial time. That was a challenge posed by Aldous and Phil in '94. Okay, so I want to tell you, what was known on this challenge before. And okay, so the maximal heating time, call it H max, is certainly a lower bound for the cover time. Now Matthews in '88 proved an upper bound, which is H max up to a log, and also related lower bounds. So one thing I want to prove to you is this Matthews upper bound. So if I could have the lights, can we turn on the light? I want to use the board for a minute. Okay, so this is I think a very clever argument by Matthews, and which you can all go back to your undergraduate classes and teach once you see it. And it's still very nice because it involves an additional randomization. So again, the statement is that the cover time is upper bounded by the maximal heating time, actually times a harmonic series like that. Okay, so to see that, let's take the set of vertices of the graph. Okay, so fix the starting node. V0. Now take V, which will be V0, together with V1, V2, up to Vn minus 1. But I want to take these in random order. Okay, so I fix the starting node V0, but then all the other vertices, I have n minus 1 other vertices, I put them in a random order, so add a random permutation. And this is I think the beauty of Matthew's argument. We have a random process, the random walk on the graph. He introduces an additional randomization, which, as we'll see, will aid in the calculation. Okay, so you take these vertices and order them. And then you define variables tk, which is the time. I'll write it there. Maximum of tau v1, tau v2, up to tau vk. And to remind you, tau v is the first time we visit v. Okay? So tk is the first time where we visited all the vertices v1 up to vk, which were chosen in this random order. So what's the expectation of t1? Well, certainly for t1 it's just hitting v1, so certainly that's bounded by h max. Okay, now let's try to bound a typical increment. So expectation of tk minus 1. But let's first do that conditional on the sigma field of everything that's happened until time tk minus 1. Okay, so this is the sigma field of all events that are measurable with respect to the process until time tk minus 1. And we're conditioning on the sigma field and looking at the expected time from, so of course tk minus 1 itself is measurable here, but then we're looking at the additional time until tk. Well, this additional time, there are two possibilities here. One possibility is that, so look at tk minus 1, it's the time until we visited v1 up to vk minus 1. One possibility is that by that time we have already visited vk. There's nothing that's stopping us from doing that. And if we've already visited vk, then additional time is 0. So we get the contribution only in the case that tau vk is bigger than tk minus 1. And I want to write here an upper bound. So only in this case we get the contribution. In this case, what is the contribution? It's going to be the time from the vertex that we've reached to vk. So maybe I'll write it still as an equality. So this is this indicator multiplied by the, running into lack of space, so multiplied by the expected time from the vertex we are at, which is x at time tk minus 1 of vk. Right? If we still have to visit vk, then we look at the vertex we are at, and we have to hit vk. So the point is that this is bounded by the indicator of tau vk bigger than tk minus 1 multiplied by h max. Right? Because this hitting time, it's from an unknown vertex to another unknown vertex, but it's certainly bounded above by h max. So once we know that, we can just take expectation of that and get that the expectation of this increment tk minus 1 is bounded by h max times the expectation of this indicator. And they claim this expectation of this indicator is 1 over k. And here the additional randomness that we have in the random permutation is playing a key role, because what is the expectation of this indicator? Just the probability that of this event. And what is this event? It exactly means that among the vertices v1 up to vk, the vertex vk is the last to be visited. Right? But the vertices are in random order. So among the vertices v1 to vk, the random walk is walking, and there's somehow condition on the random walk. There is some last vertex to be visited. Think of after that you do the random permutation, then the chance that the random permutation will choose this last vertex to be visited to be called vk is exactly 1 over k. Right? So again, you condition on the random walk, and you condition in the random permutation which are the first k nodes, but leave free the choice of how they are internally ordered. Then the chance that vk will be chosen to be the last vertex to be visited is exactly 1 over k, because we have a random permutation. So this gives this formula, and now we are done, because just summing these over all k will give you this formula, because notice that that t kav is exactly the expectation of Tn minus 1. Okay, so by time we reach Tn minus 1, the random order no longer plays a role. We have to visit all the vertices, so we exactly get the cover time. So just add this telescoping sum, and you get this upper bound. Now, besides the nice formula, so this formula estimates the cover time up to a factor log n by a known quantity. The maximal hitting time is something you can compute, but you have this uncertainty of a factor of log n. Now, the same technique of Matthews also gives you a lower bound, because remember, this calculation here was exact. Up to here it's an identity. So what you could do is also get a lower bound by saying, well, this expectation is at least the minimal hitting time. Okay? This expectation is at least the minimal hitting time. And so you can get a similar lower bound for t kav, replacing h max by h min. Okay, so you'd get a lower bound. But now let me go back to the slides. Sorry. I'm going to... Yes. Okay. Now, but the lower bound here with... Okay, so I said you can get a lower bound replacing this h max by h min. But that's not usually so useful, because the minimal hitting time is too small. Usually between neighbors, the hitting time is very small. So Matthews already suggested the following trick. If we want to cover the whole graph in particular, we have to cover every subset. So choose some nicely separated net in the space. So some set which is still has many points, but not too close. Okay, there is some engineering to do to choose this set. And then you can use the same idea to bound the cover time from below, just using the cover time of this special set. And that gives you the following. So for any set S, you can take the minimal hitting time within the points of the set, but then the factor you get, instead of being log n, it would be log of the size of the set. Okay, the same argument just applied to a subset will give you that. And since it's true for any subset, you can maximize over the subset. Okay, so this was still in Matthews' 88 paper, very ingenious and simple arguments, and Kan-Kim, Lovas, and Vu then analyzed this Matthews argument more carefully, introducing some new ideas, and showed that the lower bound that Matthews gave, so this lower bound, is sharp up to a log n squared. So as long as you're willing to maximize over all sets. Now, when you look at this maximum, you first might worry, well, this doesn't look computable because these are too many sets. But in fact, there is a dynamical programming or recursive algorithm to compute this maximum. So in fact, they gave an algorithm that estimates the cover time up to this log n squared, which, in practice, log n squared never is too big, but it does go to infinity. And this was the state of the art in 2000. I won't give you the details of the argument, but I'll give you some elements soon. Now, Feige and Zeytouni showed that for for trees you get a good approximation. I'm not. So for trees there is some special recursive structure that helps you. Okay, now I want to go to blanket times. So Winkler and Zuckerman in '96 looked at the following question. So if we look at the cover time, say of a complete graph, so we have coupon collector, at time n log n we cover the complete graph. At that time, one vertex is visited exactly once, the last vertex we hit, but typical vertices are visited log n times. So there is a big discrepancy between these occupation numbers, and Lovas and Winkler Winkler and Zuckerman were interested in, well, how long until we get a balance of the local times? That the number of visits to a site is about the same for all nodes. Now we have to be a little bit careful, because if we run time to infinity, the asymptotic number of visits to a vertex is proportional to the degree. So the right thing to equalize is not the number of visits, but the number of visits normalized by the degree, and that's what we are going to call the local time. Number of visits to x divided by the degree of x. And as time tends to infinity, just any version of the ergodic theorem or the law of large numbers will tell you that the local time ratio between any two nodes is going to tend to 1. But that's the asymptotic version, and they asked how long till this ratio is, say, less than 2, or any less than beta. How long does that take? We have to wait until the cover time, but do we have to wait till a large multiple of the cover time? So they analyzed a few examples, like for the complete graph, you just wait for twice the cover time and you're fine. And then they looked at the cycle and just one or two more examples. In all these examples, a constant multiple of the cover time was enough. And then they conjectured that in general, the cover time, we have some, that in general the cover time is bounded by, I don't know what happened to the fonts here, that the cover time is bounded by the, let me try and improve the file here 1 second. Okay, so I think this version will look better. Sorry. Okay, so I'm sorry, I have to switch these versions just because of font issues. Okay, so right, so they conjecture that the cover times and the blanket times are equivalent, and Kan, Kim, Lovas, and Vu proved that this is true up to the log n squared factor, because they proved that their upper and lower bounds for the cover time also apply to the blanket times. So this implies this connection. And this was actually one of their main motivations, is to try and verify this Winkler-Zuckerman conjecture, that the blanket time is equivalent to the cover time. Now, another place where cover times were analyzed was for random graphs. So look at the Erdős-Renyi random graph, GNP, where P is constant over N, with C bigger than 1. Then Cooper and Fries analyzed this in great detail. It's I remember struggling to read this paper, and then going to Alan Fries and asking him, why was it so hard to read? And he tells me, well, I write my papers to record the result, not to be read. So anyway, so the cover time is asymptotic to n log squared n with a constant. So this is actually not hard to show, but identifying the constant is hard. And they found the constant, how it depends on C. And as C tends to 1, psi of C also tends to 1. So this might suggest to you that if you take the constant here equal 1, you'll get a cover time of n log squared n. But this interchange of limits should be viewed with suspicion, and in this case it's actually wrong. So in the critical case, it turns out that the critical random graph, the largest component is very close to a uniform random tree on n to the 2/3 vertices, and the cover time really has different asymptotics. So this motivated work with Martin Barlow, Jian Ding, Asaf Nachmias, where we analyzed, again in great detail, the cover time of near critical random graphs. I won't tell you the details of this, but the point is we understood how the transition happens between the supercritical and the critical cases, and in order to analyze it, we had to use some methods that Martin Barlow had developed earlier to analyze local times of stable processes, Levy processes. So we really were looking at the classical theory of local times for Markov processes. And in particular, in order to analyze this, the reason I'm telling you this story is we finally did some kind of multi-scale analysis to bound the cover time. So the idea is to upper bound the cover time. One way to upper bound the cover time is to ensure that all the local times are positive, right? So that means that you've covered. Now, think of the local times as some kind of surface, and you want this surface to be positive. How are you going to guarantee it? Well, you want to show that this, of course, this is a surface over a discrete space. But you want to show that this surface doesn't have too much variation. So you want to show that it's, because we're going to run to a large enough time that we know that the local time at some specified node is high. And then we want to know that all the local times are large. So we want to show that the local times don't vary too much between different nodes. And so, so somehow it's natural that entropy ideas come in. So if here is some notation, ns d epsilon, the minimal number of epsilon balls in a metric to cover a set. R is the diameter in the resistance metric. So remember, I told you the resistances form a metric before, because they're essentially the commute times. So if R is the diameter in the resistance metric, and so you look at the number of balls of radius r epsilon needed to in this effective resistance metric needed to cover your vertex set. You take the square root of the log, integrate that d epsilon, and this gives the, after squaring and multiplying by these constants, this upper bounds the cover time. So I won't give you now the details of it, but you'll see something about where these ADs appear in a moment. And this actually refines the results of KKLV, Kant, Kim, Lorenz, and Wu. It allows you to reproduce their log n squared bound. And again, this upper bound also applies for blanket time. So after we did that, and the specific goal we had was to analyze these near critical random graphs, but in the process we got this general bound. And once we finished that, I looked together with Jan at this bound, and they said, this bound looks familiar. After all, this is, for those who know Gaussian processes, this is essentially the Dudley bound for the maximum of a Gaussian process. And okay, so in 1967, from the early 60s to the 90s, or to 1990, there was a lot of 30 years of activity on trying to get very precise bounds for Gaussian processes, usually over very fancy spaces, in order to understand continuity and boundedness properties of these Gaussian processes. And one key bound, early bound, but very effective, is this Dudley entropy bound. So it says that, and I'll tell you something about it, but it tells you that the supremum of a Gaussian process can be bounded by some kind of n. So remember, ns d epsilon is the number of balls in radius epsilon needed to cover a metric space S in a metric D. And I'll say a moment, this metric D is the natural metric for the Gaussian process. It's just the L2 metric between the Gaussian variables. And this was the Dudley 1967 bound. And you see that it's very close, up to some squaring and these constants, to the bound we got for the cover time. Now, in the Gaussian process, there were another 20 years between the Dudley bound and the optimal bound found by Talleyrand. But if we know the history, we don't have to repeat it. We can maybe benefit from it. So this was the idea, that this connection cannot be an accident, and maybe just the Talleyrand theory can be transferred to this setup. Okay, so after the Dudley bound, Fernique and Talleyrand characterized the maximum of a Gaussian process exactly using the notion of majorizing measures. So indeed, this connection worked out. That's what I want to tell you about next. But to make this connection precise, I have to talk about a specific kind of Gaussian process, which is, luckily for all of us, important in many branches of modern probability, namely the Gaussian free field. So this is a picture I got from Scott Sheffield of the Gaussian free field in square lattice at finer and finer scales. And as many of you know and have heard, there's a close connection for the level sets of the continuum Gaussian free field to SLE. I'm not going to talk about that here, but rather about the discrete Gaussian free field, a more elementary object. And it can be defined on any graph. We're going to look at it on finite graphs. So it has many equivalent formulations. And this is maybe a sign of its importance. Okay, just like, they say that the Eskimos have many words for snow because it's important for them. So we have many definitions for the Gaussian free field. So one is it's a Gaussian process, and the variance of the difference of the Gaussian process at 2 points is the effective resistance between the 2 points. Okay, and this only tells you the height difference. So to fix the process, we fix a node V0 and make it 0 there. Okay, so this completely specifies the process. Here is another formula which turns out to be equivalent, though it takes a couple of lines to verify the equivalence. So a Gaussian vector, a Gaussian process, is completely specified if you know the covariance structure. And the covariance structure for this process is as follows. If you have two nodes x and y, the covariance of the Gaussian free field at these 2 points is the green kernel at x and y for the random walk killed at V0. So what is this green kernel? You start a random walk at x, you kill it when it visits V0, and you count the number of visits to y, normalize that by the degree of y. So this normalization will make the green kernel a symmetric function. It's positive definite, and hence there is a unique Gaussian process with that as covariance kernel, and that's the Gaussian free field. Let me give you another definition quickly. So if you have a tree, the Gaussian free field is very simple. On a tree, the Gaussian free field is just a branching random walk with Gaussian increments, what you may remember from Ofer's talks last week. So on a tree, you just put independent Gaussian variables on all the edges, and then you just add them up. So okay. So yeah, you don't. Okay, I'm just going to draw this for 1 second. So you have a tree, any tree. It doesn't have to be regular. You put, say, V0 is here. You put independent IID Gaussian variables on the edges, and then to determine the value of the field here, you just add the Gaussian variables along the path. Okay. Now, if you want to repeat the same definition on a general graph, it's also tempting to do that. So you can take a vertex. So suppose we have some cycles. So we want to define it to be 0 at V0, and for every point here, say this point, to just add the Gaussian variables along a path from V0. What's the trouble? We have inconsistencies because this path could give one value and this path could give another value. So the way we solve this problem is we just assume that it doesn't exist. That is, we condition this sum to be the same as this sum. What this amounts to is conditioning that along any cycle, the sum of the Gaussian variables along any directed cycle must be 0. Once you insist on that, then this definition is consistent. And this conditioning, in the Gaussian case, conditioning can always be done by projection. So this conditioning can be done explicitly, and it gives you, again, the same process I described before. And there are 3 or 4 other equivalent definitions, which I won't go into. So that's the Gaussian free field. And all right, so I'm going back to the slides. Sorry. Okay. And then our main result is that the cover time is up to universal constants, the number of edges in the graph times the expected maximum of the Gaussian free field squared. And this is also equivalent to the blanket time up to a constant which depends on beta. Okay, so in particular, this answers the Winkler-Zuckerman conjecture. They were right, despite they only knew it for 2 or 3 examples, and they conjectured it for all graphs, and they were right. That the cover time and the blanket time are the same.
Do you mean
up to constants? Yes.
the constant doesn't depend on the graph?
That's right. Right. Universal constants, they only depend on beta. Okay, they scale like 1 over 1 minus beta squared, but okay. So, all right. So this is the main result. So the cover time, which is completely defined in terms of a random walk, is equivalent to up to constants to this maximum squared of the Gaussian free field, completely defined by the Gaussian free field. Okay, so let me give some. I'm not going to be able to give you a full proof of this. I'll give enough indications where you can see at least where the upper bound is coming from, and I'll give a 5-minute kind of crash course on a maximum of Gaussian processes. So consider any Gaussian process. It comes with, as I said, a natural metric, which is just the L2 metric between the Gaussian variables. So again, the classical problem is what's the expected maximum of the Gaussian process, and the focus of much of the activity of the in the 60s to the 80s was to understand Gaussian processes over quite complicated spaces, and the focus was to understand when they were bounded, when they were continuous, and to do that one looked at the process over suitable nets and made some estimation over these nets. In our setting, we're interested in the process over a discrete set, but still those techniques will be useful. Okay, so what is the maximum of the process over this finite set? So again, we say Gaussian process, but the time index set is not time for us, it's the vertices of a graph. Okay, and after a lot of work, what Fernick and Talleyrand established is a formula, a deterministic formula, which is equivalent to the maximum of the Gaussian process. I'll give you this. Well, this formula has in it a lot of soups and infs, and I'll give it to you in a moment just for completeness. But the main point for us right now is that this is a completely deterministic quantity. There's no randomness in it. Okay, and it's, on the other hand, it's equivalent with universal constant to the supremum of the Gaussian free field. Okay, and so actually Fernick proposed the formula and proved one direction. Talleyrand proved the full equivalence. So because of this theorem, our theorem can be interpreted as follows. The cover time for a graph is equivalent up to constants to this number of edges times the gamma 2 functional, the majorizing measure functional of the set of vertices where the metric, remember the natural metric for the Gaussian process is going to be for us the square root of the effective resistance metric. So here's a quick comment. For any metric, if you take the square root, you get another metric just by concavity. But when you take the effective resistance metric, something special happens. If you take the square root, you get a Hilbert space metric, because you get exactly the L2 metric between the elements of the Gaussian free field, which is a Hilbert space metric. So that's a special property of the effective resistance metric. Okay, so this is another equivalent statement of our main theorem. Now, gamma 2 was given by the deterministic formula, as that the original formulation by Fernick and Talleyrand has soups and infs over exponentially sized spaces, but there is some recursive procedure, recursive algorithm that allows you to compute this gamma 2 in polynomial time. You can see the details in our paper, but I'm not going into them. But because of this, we answer the question of Aldous and Phil that there is a polynomial time procedure to give an approximation for the cover time up to a constant. Okay, it's still open to do this, to compute it exactly or to estimate it even up to 1 plus epsilon. But up to a universal constant, we can estimate it. Okay, so here's a little more background on the maximum of a Gaussian process and the analogies with cover time. So you want to understand the maximum of a Gaussian process. Well, one way to estimate the expectation of the maximum is to understand the tail of the maximum. So what's the probability that the maximum is bigger than something? Now, again, think of these nodes as representing the random variable, and these distances are the L2 distances between the Gaussian variables. So if all the distances are large, so all the variables are roughly independent, then you can just use the union bound. And if you have, so for instance, if you have k independent Gaussian variables, their maximum, standard Gaussian variables, the maximum is of order square root of log k. Now, if they are not exactly independent, but their distance is alpha, then you can get that the maximum is alpha times root log k. So the key to get that as an upper bound is to just use the Gaussian concentration inequality. So this is just the, coming from the tail of a Gaussian variable, very elementary thing. Remember that this du v squared is just the variance of the difference. So just use that Gaussian concentration and the union bound. Okay? Now, a non-trivial fact is, but let me say that this root log k turns out to be analogous to the log n you saw in the Matthews upper bound. And there is a corresponding lower bound known as Sudakov minoration that says if you have a bunch of Gaussian variables and all the pairs are separated by at least alpha, then the expected maximum is at least alpha times square root of log of the size of this set. And this corresponds actually to Matthews' lower bound, where we had a lower bound on the hitting times between the different points. Now, how does one get better upper bounds for the maximum of a Gaussian process? So I said before, if all the points were kind of separated far apart, you could just use the union bound and essentially that's sharp. But suppose your metric space has this structure where we have a bunch of clusters that are separated from each other, but each cluster is kind of close together. Then it's very inefficient to use the union bound because these variables here are all very close, very correlated. So if one is large, then the others tend to be large. So using a union bound is very wasteful on highly correlated events. So a natural trick is to do the following. Let's first bound these gray points. They are essentially independent, so we can do that using a union bound. Once we control those, let's control just the differences between the gray points and the red points. These differences are have very small standard deviations, so we can control them effectively. And by combining these, we can get good bounds on the maximum at all the gray and the red points. Okay, so this is the natural approach known as chaining. It really goes back to the first use of that I know of is Kolmogorov's continuity theorem that many of you see in basic courses. So that's kind of a natural approach. And if you do that consistently using just epsilon nets in the space, you will get the Dudley entropy bound. Okay, so you just first take epsilon equals 1, then pick the gray points. I just drew the tree to depth 2, but of course near these red points there could be other green points clustered around them and so on. So you could have a tree of high depth, and the Dudley entropy bound can be proved just by building this tree and using epsilon nets where epsilon goes to 0 and using those epsilon nets as the nodes of the tree. It turns out that this is a very efficient bound in kind of spaces that have symmetry, but if your space is very asymmetric, it has high density in one area and low density in another, then just using epsilon nets is too crude. So the Fernic-Talagrand bound can be thought of as still using the same idea, but saying let's optimize over the choice of tree. I don't have to use epsilon nets. I can use any tree I like, and then there's still a challenge how to optimize these trees, but you can still do it using some dynamic programming or just huge soups and infs, and then the beautiful thing is that you still get an upper bound. You still get, it's very simple to prove the upper bound, but the beautiful thing is this now is sharp. Once you optimize of the tree, you get something which is right up to universal constant on all Gaussian processes. So this is not trivial at all. Here is the formal definition of this gamma 2, and if you know it, then you don't have to see it. If you don't know it, then it's still not going to be useful for you to see it. But for completeness, I'm showing it anyway. So you have a metric space. Given a partition, P of x is the unique point containing, P of x is the unique element of the partition containing x. Now you take what corresponds to these trees is an admissible sequence of partitions. So again, this is one formulation you can write explicitly in terms of trees, but here I chose the partition definition. So ak plus 1 is a refinement of ak. The size of ak is bounded by 2 to the 2 to the k. So this doubly exponential bound. And then the gamma 2 function is defined as follows. You take infimum over all these collections of admissible partitions. And then once you fixed your partitions, you take the sup over all points of the space of this kind of sum. So you look at ak of x, which element of the partition contains x in the kth partition, like the diameter of that, and add these with coefficient 2 to the k over 2. Now, the only thing I want to comment is this 2 to the k over 2 corresponds to the square root of the log of this 2 to the 2 to the k. So you see the square root log that we had before is still hidden in this formula. And okay, the formula looks daunting, but the idea is just the optimizing over trees idea that I told you in the previous slide. That's really the useful thing to remember. Any questions? Okay, let me comment that Talleyrand has a book, The Generic Chaining, which kind of explains this. And there is a less complete, but perhaps a very illuminating explanation in the blog of James Lee, which it's called TCS Math, and he gave explanation of this Talleyrand bound. Anyway, let me continue on the analogies with the local time. So remember the Gaussian concentration bound. Now, Kahn, Kim, Lovász, and Wu, to prove their estimate, also the first step was a concentration bound, which looks very similar. They didn't notice the connection. Now, what is their bound? You say they look at the local time at u minus the local time at v. The probability this is bigger than alpha has this bound. Now, how long do they run? You run until the global time, t. Well, I'm sorry, you run until the local time at the vertex u is a number L. So you run until the number of visits to u is L times its degree. Then you stop. And you ask, what's the chance that the local time at u minus local time at v is large? So this, remember, corresponds to this idea of the local times as a surface, and you want to say that control its variation. So you want to say, if we have two vertices, we already assume that the local time at u is large. What's the chance that the local time at v will drop far below? Well, the chance is not too big. And this is actually very easy to prove if you think of excursions, right? So if you think every time you visit, think of the walk in excursions going back and forth to u, the number of visits to v in each such excursion is independent, because these are independent excursions. And it has a very simple distribution. If we start at u, how does the number of visits to v behave? Well, first we have to visit v, and then the number of visits to v will be geometric. So the number of visits is an indicator times a geometric variable. Very simple distribution. And we just have a sum of IID variables with this very simple distribution. So just the simplest large deviation bound will work here. You just apply Laplace transforms. And when you do that, you get this bound in KKLV for this difference of local times. But it comes out to be very similar to the Gaussian concentration, where the effective resistance scaled is representing the Gaussian variance. So you see that if you look at these two formulas, you see, well, to make this analogy work, I want to have a Gaussian process where the distance in the Gaussian process, the variance, corresponds to the effective resistance. And that's where the Gaussian free field comes in naturally. Okay. Now I told you about Sudakov minoration. going back to 1973, Matthew's lower bound in 88 is essentially the same up to the squaring. So you see that you get a bound which involves here the square root of the log, here the log. And this corresponds to the cover time, remember, is related to the square of the Gaussian free field. Now, the whole story of lower bounds is much harder than the story of upper bounds. And you see, for upper bounds, it's enough to control the pairs, the pair distribution, in order to upper bound the whole process. For lower bounds, that doesn't work. You can see this from a simple example. Take a standard Gaussian variable and IAD random signs and multiply xi as x times xi. This, of course, is not a Gaussian process, but the techniques for upper bounding for Gaussian process work very nicely for this type of process, because all these techniques used was the bounds on the tails of the differences. But for lower bounds, this really doesn't work, because this process has, the expected maximum is just given by the maximum of the original variable x. So it's just, you just get the maximum of one Gaussian variable. So in order to prove lower bounds, you have to use more of the Gaussian structure, not just the pair distributions. Okay. Now, the link we use between Gaussian and Gaussian processes and local times comes from the Dynkin isomorphism theory, more specifically a variant due to Eisenbaum, Caspi, Marcus, Rosen, and Xi. And that's, again, something that was applied until recently. It was, as far as I know, never applied to discrete spaces. The point of this Dynkin isomorphism theory was to obtain continuity results for local times of Markov processes in very general spaces from the corresponding results for Gaussian processes. But the bounds and the connections obtained were so sharp that they are useful for quantitative estimates in discrete settings. And this can be viewed as a generalization of the classical Ray-Knight theorem for Brownian motion. But here is an identity in law due to, as I said, Eisenbaum, Caspi, Marcus, Rosen, and Xi. And until now, there is no. Okay, so this identity in law is, there is a proof of it using Laplace transforms. There's no real probabilistic understanding, although recent ideas of Lejeune suggest that we might soon have more probabilistic understanding of this. Okay. Anyway, what is the identity? It's really kind of a beautiful identity. So I'm not going to express it in the most generality, just for the case we need of the Gaussian free field, but you'll get already the flavor. So fix a vertex V0, and one change I'm already going to make is I'm going to switch to the random walk in continuous time. So instead of working in discrete time, each step we're going to wait for an exponential time of mean 1, and then jump to a uniform point. This doesn't have any effect on the expected cover time, just because the expectation of the time to make a step is still 1. So the expected cover time doesn't change, which is our goal. But the local times do change. The local time now is the time we spent at a node divided by its degree. But this time is now a continuous quantity. And this is essential if we want to relate it to Gaussian variables, which are also continuous quantities. I want this relation to be based on identities, not just estimates. Okay, so we are switching to continuous time. And then T of L is the first time that at the node V0 we accumulated local time of L. Okay, so we visited V0 for the amount of time we waited at V0 was L times its degree. We wait until that time, and that's when we stop. And then we're looking at the whole local time field LXT, so that tells us at that moment how much time did we spend in each vertex X normalized by its degree. That's LXT. Now, this, besides the random walk, we also have an independent Gaussian free field. So again, these two, on the left-hand side, these are independent of each other. And we add the local time and half the square of the Gaussian free field. And then here is the amazing identity. This is equal in distribution. This whole joint distribution is the same as the following. on the right-hand side, there is no random walk, just the Gaussian free field. We take the Gaussian free field, we shift it down by root 2L. So remember, L was our stopping criterion. We shift this Gaussian free field down, we square it, take half, and these two things are just have the same joint distribution. And until now, the only proofs are based on writing Laplace transform of both sides. You get ratios of huge determinants, and you can find there is a book by Marcus and Rosen on these matters, so you can find these huge determinants there. And then you observe that these determinants on the left and on the right are the same. So the way these kind of identities were, are still at this point hard to discover. There are many other related identities. They're kind of discovered by trial and error and then verified by calculating huge Laplace transforms. But, all right, so this is the identity, and I want to indicate to you how this identity gives us actually the upper bound for the cover time in terms of the Gaussian free field. The lower bound I won't be able to really go into. All right, so we have this identity, which I'll recall for you in a moment, and we want to prove an upper bound for the cover time, or I'll even do more and give an upper bound for the blanket time. So we want to bound it by the number of edges times the square of the expected maximum of the free field. So what do we need to show? We need to show that if the time is much bigger than the number of edges times the expected maximum squared, then we want the local times to be about uniform, right? And that will indicate that we have reached the blanket time. Okay, so all right, so we want the time to be this large. So how big should the local time L be at a specific node V0? We have to scale it down. So we have to scale it down by the number of edges. So to go between the global time and the local time at the node, we have to divide by the number of edges. And so the claim boils down to the following. If the local time at V0, which we will denote by little l, is much, much bigger than the expected maximum squared of the field, then the local times are beta uniform with high probability. Okay, so I will show you how we verify that from the Gaussian free field, and then okay. So this is what we want, and what we'll use is this identity in law. Take the right-hand side and just expand the square. So we get this. So we have this identity in law. And now in order to see how we use it, we have to see in this, there's lots of symbols here. We have to see which are big and which are small. And then it will be clear that we've reached the blanket time. So how do we see which is big and which is small? Here's one way. So we're going to... So I told you that we run, right? So here, I told you that we run to local time, which is much bigger than the square of the maximum of the Gaussian free field, okay? So this local time L is much bigger than all these Gaussian squared variables, okay? So we have till 12:15, is that right? That's 12:15?
You have 5 minutes.
Yes, 5 minutes, okay. So, all right, so this local time L is much bigger, chosen to be much bigger than the square of the Gaussian free field, and hence it's also bigger than the geometric mean of L and this square. So this number is bigger than these two things. So they can be thought of as a perturbation of L. So L is a constant, and we're perturbing it by these small variable things. On the left-hand side, we have the local time field, which is what we want to understand, and it's again perturbed by something small. So of course, this formula means that here we take this constant with a small perturbation. Here we have an unknown field with a small perturbation. So this unknown field must be approximately constant, which is what we want. We want to show that when we chose this little l this large, then when we chose L this large, the local time field is approximately constant, namely we reach the blanket time. And it just follows from the isomorphism theorem. So the upper bound, again, is easy. Now, it turns out that the lower bound on the blanket time is also easy if you use So I don't have time to show you the details, but I'll just say that it follows easily from something known as the Borel-Tsirelson isoparametric inequality, which tells you that the maximum of a Gaussian process is concentrated. Its variance is no larger than the variance of the individual variables. So if you just use that, you can get a lower bound on the blanket time from the isomorphism theorem. So I told you that the upper bound and the lower bound on the blanket time can be obtained really just from the isomorphism theorem, actually without using the Talleyrand theory at all. So where do we need the Talleyrand theory? Well, 99% of the work is actually getting a lower bound for the cover time. The difference with the cover time, we have to distinguish between local time, which is 0, and tiny. While for blanket time, it's more robust. We have to consider when the local times are large. So considering when the local times are 0, distinguishing that is really much harder because of the nature of the isomorphism theorem. And this really involves a full use of the majorizing measure theory and further concentration bounds. In view of the time, I'm not going to go into the details, but we had to use electrical network theory. And one crucial thing is, if you look at the maximum of a Gaussian process, then the known concentration inequalities tell you that there is, one of the Gaussian variables is close to the maximum, but this is not close enough for us. And really, we have to use the fact that if you go down to a small constant times the expected maximum, then you have many variables that approximate that value. And we had to use ideas from percolation on trees. Basically, we had to use everything I've been studying for the last 20 years in order to actually make this proof work, which suggests that there should be maybe a more streamlined proof, but we're still looking for that. Now, as I told you, our main result estimates the cover time up to a constant factor. What about more precise asymptotics? So again, the upper bound is easy. So remember, this is the quantity I told you is asymptotic, is equivalent to the cover time, the number of edges times the expected maximum squared of the field. And I told you before there's a constant here, but in fact the constant can be replaced by 1 plus lit O of 1, assuming the cover time is concentrated. So if the cover time is bigger than the hitting time, so think of a sequence of graphs where the hitting times are negligible to the cover times, then you can bound the cover time by this quantity that we had before with the 1 plus lit O of 1. And in the paper with Jian and James Lee, we conjectured this was also true as a lower bound. And based on various examples which are known, like complete regular trees and discrete tori, and this was recently proved in the case of bounded degree graphs by Jian Ding. He proved that, again, if the hitting time, what we called before H max, is little O of the cover time, then the cover time is really asymptotic to the number of edges times the squared maximum of the Gaussian free field. But unfortunately, he could only show it for bounded degree graphs and not in the generality of our general theorem, so that's still a challenge. Let me say that there are now, after this, there are many further connections that are being explored between local times and Gaussian processes in graphs. And basically, any question you have on random walks on graphs, it's worth looking, can you use the isomorphism theorem to express it as a question about Gaussian variables? Because, I'll just finish with this remark. If you have a random walk on a graph, and you condition on the local time at the vertex, that's still easy to understand because you can think, okay, I fix how many times I visit this vertex, and then I have excursions from that vertex, and I can understand the whole structure. But if I have 7 vertices, and I condition on the local times in all these 7 vertices, then I'm lost. Okay? However, if we go over to the Gaussian picture and I take 7 vertices and I condition on the values of the variables on all these 7 vertices, we're still in good shape because it's still just a projection. So that's why moving over to Gaussians is effective. Thanks for your attention.